Space looks empty, silent, and still. But its cold is far stranger than most people imagine. In some places, space is only a few degrees above absolute zero. In others, sunlight is blazing, yet the vacuum stays empty and unforgiving. Tonight, this journey moves from the edge of the universe to the motion inside atoms, revealing the shocking truth about how cold space really is. If this kind of calm cosmic exploration belongs here, please like the video, subscribe to the channel, and settle in for the full story. Space is not simply cold in the ordinary sense of winter air or frozen ground. It is cold in a more stripped and universal way. Across the vastest reaches of the cosmos, far from the warmth of stars or the thin veils of gas around galaxies, there remains a faint bath of radiation that fills all directions almost evenly. This radiation is known as the cosmic microwave background. It is not a local feature of one star system or one galaxy. It is not produced by one recent source. It is the remaining thermal glow of the early universe, stretched, weakened, and cooled over immense spans of cosmic expansion. In the broadest outer setting, this is the nearest thing the universe has to a baseline temperature. That temperature is about 2.7 degrees above absolute zero on the Kelvin scale. Absolute zero is the limit at which the random motion associated with heat reaches its lowest possible state. Space does not quite reach that limit. Even in the deepest darkness between major structures, the background radiation still carries little energy. It is extremely faint by human standards, yet it is real, measurable, and present everywhere that telescopes can look. This is why the cold of space is not perfectly empty of heat. A small remainder persists, spread across the cosmos with remarkable uniformity. The origin of this faint warmth lies in a much hotter past. The early universe is dense and bright. Matter and radiation are tightly linked, and light cannot travel freely for long before scattering from charged particles. As the universe expands, it cools. Eventually it reaches a stage in which electrons combine with atomic nuclei to form neutral atoms. Once that happens, light moves much more freely through space. The radiation released at that time does not vanish. It continues to travel, and over billions of years the expansion of the universe stretches its wavelengths. Light that once carries much higher energy becomes microwave radiation. The glow remains, but its temperature falls dramatically as the fabric of space itself expands. This background is one of the most important clues in modern cosmology because it shows that the universe once exists in a much hotter and denser state than it does now. Yet in this section, it serves a more immediate purpose. It defines what it means to speak of the cold of space on the larger scale. When there's almost nothing else around, no nearby star pouring out intense light, no planet re-radiating absorbed heat, no dense cloud trapping energy. The cosmos still contains this faint thermal field. It is everywhere, and it gives the emptiest parts of the universe a minimum radiative environment. The word temperature can be misleading when applied to space, because empty space is not a solid object or a pool of fluid. Temperature usually describes the average energy of particles in matter, or in some contexts the energy distribution of radiation. In the case of the cosmic microwave background, the temperature refers to radiation itself. The spectrum of this radiation matches the smooth pattern expected from a body in thermal balance, what physicists call a black-body spectrum. That pattern reveals a temperature with great precision. The number is small, but it is not arbitrary. It is a physical measure of the energy carried by the background radiation that fills the observable universe. This makes the cold of the cosmos different from ordinary experience on Earth. On Earth, a cold day still contains enormous numbers of air molecules moving, colliding, and exchanging energy. In the broad cosmic background, matter can be so sparse that those familiar forms of heat exchange hardly occur at all. The background radiation does not feel like a wind or a frost. It does not sweep over skin or flow through rooms. It simply exists as a thin field of ancient light. An object placed in an otherwise empty region will interact with that radiation, absorbing a little and emitting its own. In the very deepest cosmic quiet, that exchange sets a natural reference level. The near uniformity of the cosmic microwave background is also significant. Measurements show that its temperature is almost the same in every direction, with only tiny variations. These differences are very small, only a few parts in 100,000. They matter greatly for the history of cosmic structure because they reflect slight differences in density in the early universe. But as a thermal backdrop, they reinforce a simpler point. On the largest scales, the universe is astonishingly even. Its outer cold is not chaotic, it is calm, smooth, and widely shared. That smoothness does not mean every part of the universe is equally cold in a practical sense. Local conditions can differ enormously where stars shine, galaxies cluster, or gas falls into powerful gravitational systems. Yet those are local additions laid over a broader background. The outermost cosmic environment still carries the same ancient microwave glow. It remains the quiet thermal floor beneath brighter and more active regions. In the widest view, the universe is not defined first by blazing suns, but by this dim and nearly uniform remnant from its beginning. The faintness of the background also reveals how much the universe has changed. The early cosmos is filled with intense heat. Over time, expansion dilutes that intensity. Wavelengths stretch, energy per photon decreases, the thermal field cools. What remains today is a relic that has fallen to only a few degrees above absolute zero. This is not because the universe has become dead or motionless. Galaxies still form stars, stars still heat planets, and energetic processes still occur in many places. But the larger scale trend is one of cooling. The background records that long drift toward lower average temperatures. In this sense, the cold of space is not merely an absence. It is a history. It carries memory. Every direction in the sky holds the same faint message from the early universe. Not in words, but in radiation that has crossed almost all of cosmic time. Instruments can detect it as microwaves. The human eye cannot see it, and the human body cannot sense it directly, but its presence is one of the best established facts in astronomy. It surrounds every galaxy, every cloud of gas, every drifting particle, and every quiet region where little else remains. So the outermost truth about the cold of space begins here. Space is cold because the universe has cooled from a much hotter beginning, and because what remains on the grandest scale is a nearly uniform bath of ancient microwave radiation at about 2.7 Kelvin. That cold is not perfect emptiness and not complete stillness. It is a thin residue of primordial heat, spread across the cosmos so evenly that it becomes the background condition of existence itself. In the widest possible region, before any local source changes the balance, this is how cold space really is. Beyond the large gatherings of galaxies, there are regions where the universe becomes even quieter. These are the intergalactic voids, immense expanses with very few galaxies and with matter spread so thinly that ordinary language begins to fail. A void is not an empty box with sharp walls. It is a broad region in which the density of matter falls far below the cosmic average. Galaxies become rare. gas becomes extremely diffuse, and the exchange of energy through contact becomes almost negligible. In these regions, the cold of space appears in one of its purest practical forms. A void can span tens of millions of light years. Within such a region there may still be a few isolated galaxies, faint streams of gas, and invisible dark matter shaping the large-scale structure of the cosmos. Yet compared with the richer regions where galaxies cluster together, a void is sparse almost to the point of absence. The darkness there is not produced by black walls or heavy shadow. It comes from distance, rarity, and the fact that there are simply fewer luminous sources to fill space with radiation. This scarcity matters because temperature in everyday life depends strongly on nearby matter. On Earth, warmth moves easily through dense surroundings. Air carries heat. Water carries heat. Solid materials conduct heat from one place to another. In an intergalactic void, such pathways are nearly gone. There are too few particles for frequent collisions, and the distances between them are enormous. A particle of gas drifting through a void may travel a very long time without meeting another. In that sense, voids are not only dark, they are thermally isolated. That does not mean everything in a void sits at exactly the same temperature. The concept becomes more subtle because there are two different physical realities present at once. One is the background radiation that fills the universe, already described as a faint thermal field near 2.7 Kelvin. The other is the sparse matter inside the void, mostly thin ionized gas, meaning gas in which electrons are not tightly bound to atomic nuclei. This gas can have a temperature of its own, defined by the motions of its particles, and that temperature does not have to match the temperature of the background radiation. Observations and simulations indicate that gas in many voids is very diffuse and can still be warmer than the microwave background, often because it has been affected over cosmic time by ultraviolet radiation from galaxies and quasars, or by the general heating that occurs as structure forms in the expanding universe. Yet even when such gas is warmer in the technical sense, it does not behave like warmth in any familiar human way. The particles are so few and so far apart that the total heat content is extremely low. A place can contain particles moving with considerable energy and still remain, in every practical sense, an environment of deep cold because there is almost nothing there to transfer that energy. This is an important truth about space. Temperature alone does not tell the whole story. Density matters just as much for experience and for physical effect. A thin gas with energetic particles may carry less total thermal energy in a large volume than a modest amount of air in an ordinary room. In a void, the emptiness is so dominant that even where the gas is not at the lowest possible particle temperature, the region remains an environment of extreme thermal poverty. Light also behaves differently there. In richer parts of the universe, starlight, dust emission, hot gas, and energetic events create overlapping radiation fields. In a void, those contributions become weak. Radiation from distant galaxies still passes through, but it is diluted by distance and by the scarcity of local sources. The microwave background remains as the most uniform presence. Against such a backdrop, a drifting object in a void receives little external energy except that faint ancient radiation and whatever distant light happens to reach it. Without a nearby star or galaxy, there is very little to warm a surface. The size of these regions deepens the effect. A void is not cold merely because it lacks one source of heat. It lacks many sources across astonishing distances. There is no nearby atmosphere to hold warmth, no ocean to store it, no dense swarm of particles to share it. The physical environment is governed by separation. Matter is not only sparse, It is separated on scales so large that local thermal balance becomes weak and slow. Energy exchange still occurs through radiation, but it does so in an environment where almost nothing interrupts the long quiet between one interaction and the next. Intergalactic voids are also important because they reveal what the universe looks like when gravity has drawn most matter elsewhere. Over billions of years, matter tends to gather into filaments, sheets, and clusters, leaving some regions more depleted. Voids are therefore not leftovers in a casual sense. They are a natural result of cosmic structure growth. As matter moves toward denser regions, the underdense regions become more underdense still. The result is an enormous architecture of crowded and uncrowded space. In the uncrowded parts, cold is not created by an active cooling machine. It emerges from dilution, distance, and the lack of local energy sources. Even so, voids are not perfectly simple. Observations indicate that they still contain trace gas and that this gas can preserve a record of the radiation history of the universe. Astronomers study such regions to learn how matter behaves under very low density conditions and how cosmic expansion and radiation shape the thin material between galaxies. The lesson is not that voids are featureless. The lesson is that they are quiet enough for the absence of matter to become one of the main physical facts. So when the cold of space is considered beyond the broad background of the universe itself, the next great region is this realm of enormous emptiness between galaxies. Intergalactic voids are dark not because nothing at all exists there, but because so little exists there. They are cold not because all motion stops, but because matter is too sparse and too isolated for ordinary warmth to build, spread, or remain in familiar ways. In these vast hollows of the cosmos, the universe shows how deep cold develops when distance removes almost every local source of heat and leaves only a faint bath of ancient radiation, a trace of thin gas, and silence measured in millions of light years. Between the great emptiness of the voids and the brighter concentrations of galaxies, the universe arranges much of its matter into a vast connected structure often called the cosmic web. On the larger scales, galaxies do not lie in space at random. They tend to gather along long filaments and broad sheets, while emptier regions open between them. The pattern resembles threads and knots stretched across enormous distances. Much of this structure is shaped by dark matter, whose gravity helps guide ordinary matter into the same broad arrangement. Along these extended lanes, the cold of space becomes more complex, because the universe is no longer at its emptiest. Matter is still very thin, but it is less thin than in the deepest voids, and that difference changes the thermal story. The gas within cosmic filaments is often called the intergalactic medium, meaning the matter that lies between galaxies rather than inside them. In many parts of the web, this gas is not cold in the narrow technical sense of particle motion. A significant fraction is thought to exist as warm, hot intergalactic medium, sometimes shortened to a simpler label by astronomers, but the meaning is straightforward. It is gas that has been heated to temperatures far above the microwave background and far above the temperatures associated with dark molecular clouds. Observations and models indicate that much of this material lies in a broad range from about 100,000 Kelvin to 10 million Kelvin. In some especially active or compressed regions, temperatures may rise even further. At first, this seems to overturn the idea that space is cold. A filament can contain gas hot enough to emit X-rays or to leave signatures in ultraviolet light, and yet the environment still belongs to the cold emptiness of the cosmos. The apparent contradiction disappears once density is considered. Even when the particles in a filament move with substantial energy, they remain extremely sparse by ordinary standards. There are far too few of them in a given volume to produce anything like the heating effect of air, steam, or flame. The gas is hot in the language of physics, but thin in the language of experience. A region can therefore be both technically very hot and practically part of a deeply cold universe. This heating has physical causes tied to cosmic structure itself. As matter falls under gravity toward filaments and clusters, gas is compressed and stirred. Large-scale flows collide and generate shock heating, a process in which moving gas slows abruptly, and part of its motion becomes thermal energy. Radiation from galaxies and active galactic nuclei can also ionize and heat surrounding matter across large distances. Over billions of years, these effects help turn part of the diffuse intergalactic medium into the warmer and hotter phases that appear along the web. The result is a structure that is neither uniformly cold nor uniformly hot, but varied, layered, and still remarkably tenuous. The cosmic web is important for another reason. Astronomers have long known that the visible stars and cold gas inside galaxies account for only a fraction of ordinary matter expected from cosmological measurements. This ordinary matter is sometimes called baryonic matter, meaning matter made of protons and neutrons. For many years, a substantial portion of it seems to be missing from direct observation in the nearby universe. One leading explanation, supported by increasing evidence, is that much of this missing ordinary matter resides in the thin, hot gas of the cosmic web. It does not shine brightly like stars, and it is difficult to detect because it is spread over immense distances at low density. Yet its total amount may be large precisely because the web extends so far. Detecting this material is challenging. The gas is too faint in many places to image directly with ease. Instead, astronomers often infer its presence by studying light from bright background sources such as quasars. As that light passes through intervening gas, certain wavelengths are absorbed. These absorption features reveal the existence, composition, motion, and approximate temperature of otherwise hidden matter. X-ray observations also help trace hotter components of the web, especially near denser links between galaxy groups and clusters. In some cases, instruments have detected bridges of hot gas stretching between clusters across millions of light-years. These findings support the idea that the web is not only a map of where galaxies sit, but also a vast thermal environment filled with difficult-to-see matter. Yet even here, where gas can reach impressive temperatures, the larger impression remains one of emptiness. A filament is immense, but it is not crowded. Its particles are spread across distances that keep collisions infrequent compared with dense gas on planetary or stellar scales. There is no atmospheric blanket to hold warmth in the familiar sense. There is no rapid sharing of heat through a thick medium. Radiation still matters greatly, and the microwave background still persists everywhere underneath local conditions. The web adds energy and structure to the picture, but it does not erase the deeper truth that space remains a place where matter is usually too sparse for everyday warmth to exist. This is why the cold of space cannot be captured by a single number. In the cosmic web, one part of the environment is a faint background field near 2.7 Kelvin, while another part is a low-density gas whose particles may correspond to temperatures of hundreds of thousands or millions of Kelvin. Both descriptions can be true at once because they refer to different physical aspects of the same region. The radiation field is one thing, the particle motions of the gas are another. Space allows these distinctions to persist because vacuum and low density prevent rapid equilibration. In denser settings, matter and radiation often exchange energy more efficiently. In the web, the balance remains looser and more uneven. So the cosmic web marks a transition in the outer to inner journey through cosmic cold. It is no longer the profound emptiness of the void, yet it is not a crowded realm of stars and dense gas. It is a thin scaffolding of matter stretched through darkness, shaped by gravity, carrying much of the hidden ordinary material of the universe and holding gas that can be surprisingly hot without making space feel full of heat. Along these filaments, the truth about cold space becomes more subtle. Cold is not always the absence of energetic particles. Often it is the absence of enough matter, enough closeness, and enough contact for heat to gather into anything familiar. Around a galaxy there is often a region far larger than its bright visible body, a dim and extended envelope that does not shine with the clear structure of spiral arms or the concentrated glow of a central bulge. This region is called the galactic halo. The term can refer to several overlapping components, including dark matter, old stars, globular clusters, and diffuse gas. Here the focus remains on the gas, because it carries a crucial part of the thermal story. In these outer surroundings, a galaxy is wrapped not by empty nothingness, but by a vast, thin medium that holds matter, stores energy, and reveals how cold space can coexist with gas at extraordinary temperatures. This gaseous halo is often called the circumgalactic medium, meaning the material that surrounds a galaxy but does not belong to the dense star-filled disk itself. It extends far beyond the bright region that ordinary images usually show. In a large spiral galaxy, such as the Milky Way or Andromeda, this envelope reaches outward for hundreds of thousands of light years. Its boundaries are not sharp like the edge of a solid shell. Instead, the gas becomes gradually more diffuse with distance, thinning into the broader intergalactic environment. The halo is therefore not a wall around a galaxy. It is a wide transition zone, shaped by gravity, inflow, outflow, and time. The most striking feature of this halo gas is that much of it is very hot. Observations indicate that large galaxies are often surrounded by gas at temperatures of hundreds of thousands to millions of Kelvin. In the Milky Way, the hotter component of the halo is commonly described at around a few million Kelvin. In other massive galaxies, especially those with strong past activity or deep gravitational wells, similar temperatures appear in extended diffuse gas. This does not mean a galactic halo resembles a furnace in any ordinary sense. Once again, density decides the practical meaning. The particles are so sparse that even gas with very energetic motion remains an environment of profound emptiness and weak direct heating. The reason such gas becomes hot is tied to the life of galaxies themselves. Gravity pulls matter inward from the wider cosmic environment. As gas falls toward a galaxy, it can be compressed and shocked, turning part of its motion into thermal energy. At the same time, stars and central black holes affect the halo from within. Stellar winds, supernova explosions, and energetic outflows can drive material outward from the galaxy, enriching the surrounding gas with heavier elements and adding heat. The halo becomes a meeting place between inward supply and outward return. It is not simply leftover matter drifting in silence. It is part of the galaxy's larger circulation. This makes the halo important in understanding where a galaxy keeps much of its ordinary matter. The bright stars and dense gas in the visible disk are only part of the total. A substantial fraction of the ordinary matter associated with a galaxy may reside in this extended circumgalactic region. The same is true for heavy elements produced in stars. Elements such as oxygen, carbon, and silicon do not remain entirely inside the star-forming body of the galaxy. They can be carried outward and spread through the halo, where they become part of a diffuse and often ionized medium. Ionized means that electrons have been removed from atoms, usually because the gas is hot or exposed to energetic radiation. Astronomers detect this halo gas in several ways. Some of the hottest parts emit X-rays, though very faintly. Other parts are revealed by ultraviolet absorption lines when the light from a distant background source passes through the halo on its way to Earth. This method is especially powerful because the gas itself is often too diffuse to see directly. Instead, it leaves narrow marks on the spectrum of a quasar or another bright distant object. Those marks show what elements are present, how ionized the gas is, how fast it moves, and what temperature range is likely. In this way, the halo becomes visible not by its brightness alone, but by the way it alters light crossing its thin expanse. One of the clearest lessons from these observations is that galactic halos are not uniform. They contain multiple phases, meaning gas under different physical conditions in the same broad region. Some parts are cooler and traced by lower ionization states. Other parts are hotter and traced by highly ionized atoms such as oxygen missing many electrons. There may be clumps, filaments, clouds, and broad diffuse reservoirs, all moving under the combined influence of gravity, pressure, magnetic fields, and galactic feedback. This variety matters because it shows that the outer surroundings of a galaxy are not a smooth bath with one simple temperature. They are layered and dynamic even while remaining sparse. Yet despite this complexity, the halo still belongs to the wider truth of cold space. A particle within the halo may carry enough energy to correspond to a temperature of millions of Kelvin, but the halo as a whole remains so thin that it does not warm objects the way dense gas would. Heat transfer by direct contact is weak because the particles are far apart. An object placed in such a medium is influenced far more by radiation balance and by its own emission than by anything resembling immersion in hot air. The halo is therefore a region where temperature sounds dramatic in numerical terms, but remains inseparable from extreme low density. The Milky Way offers a close example. Evidence from X-ray emission and absorption studies shows that the galaxy is embedded in an extended reservoir of hot diffuse gas. This material stretches far beyond the stellar disk and joins a larger environment of satellites, streams, and inflowing matter. Andromeda shows similar signs of an extensive halo, with ionized gas reaching to large distances from the galaxy's center. These observations suggest that massive galaxies are not isolated islands of stars suspended in emptiness. They are surrounded by enormous faint atmospheres of a kind, though unlike planetary atmospheres, they are vastly thinner, hotter, and more weakly bound in any everyday sense. So in the region around galaxies, the truth about cold space becomes more layered again. The darkness beyond the bright disk is not empty, and the gas there is often far hotter than intuition first expects. Still, the halo remains part of the cold cosmos because its matter is diffuse, its contact is weak, and its immense extent is ruled by thinness rather than crowding. A galaxy shines brightly at its center and along its arms, but around that brightness lies a broad invisible envelope where heat exists without comfort. Matter exists without solidity, and space remains mostly what it is elsewhere: vast, sparse, and deeply cold. Within a galaxy, beyond the broad halo and outside the surfaces of stars, there is another region that appears empty at first glance but is not empty at all. This is interstellar space, the space between stars. In a spiral galaxy it fills the disk, stretches through the arms, surrounds stellar neighborhoods, and links one visible concentration of matter to another through a thin and changing medium. It contains gas, dust, radiation, and magnetic fields. It is so sparse that no human sense could mistake it for air, yet it is far denser than the deepest voids between galaxies. Here the cold of space is not defined by a single condition. It is shaped by the varied material that drifts between stars and by the light those stars pour into their surroundings. The interstellar medium, as astronomers call this material, is mostly gas with a much smaller amount of dust. The gas is made mainly of hydrogen and helium, with traces of heavier elements that stars have created and returned to space over time. The dust consists of tiny solid grains rich in carbon, silicon, oxygen, and other elements, built in stellar outflows and debris from dying stars. Though dust makes up only a small fraction of the mass, it has a powerful effect on light. It scatters, dims, and reddens starlight, and it absorbs energy and emits it again at longer wavelengths. Because of this, the thermal character of interstellar space is never set by gas alone. The density of this medium is extremely low. In many diffuse regions, there may be roughly one particle in a cubic centimetre, sometimes less and sometimes more. That is far thinner than even the most rarefied air near Earth. It means particles travel long distances before colliding. Heat does not move through interstellar space in the direct and familiar way it moves through dense gas. Yet because stars are embedded in this medium, their light and their winds continually shape it. The result is a region of sharp contrasts, where some areas remain relatively cool, some are warm, and some are heated to very high temperatures by violent events. This variety is one of the defining features of interstellar space. It is a multi-phase medium, meaning that gas exists in several distinct physical states at once. Some of it is neutral atomic gas, in which electrons remain attached to atoms. Some of it is ionized gas, in which energetic light or collisions have stripped electrons away. Some of it is hot and thin, filling large bubbles carved by supernova explosions and stellar winds. Some of it is cooler and denser, collecting into sheets and filaments. These phases can coexist because the overall density is low, and because heating and cooling processes operate differently from place to place. In the more diffuse neutral regions, temperatures often reach several thousand Kelvin. In warm ionized regions, they may also sit around several thousand to about 10,000 Kelvin. In the hottest thin cavities, temperatures can rise to around 1 million Kelvin or more. These values sound extreme, and in a technical sense they describe the energy associated with particle motion. But the thinness of the gas remains decisive. Even gas at a very high temperature carries little total heat per unit volume, when there are so few particles present. Interstellar space therefore remains part of a cold cosmic environment, even when parts of its gas are formerly warm or hot. Starlight plays a central role in this balance. Bright young stars emit large amounts of ultraviolet radiation, and this light can ionize surrounding hydrogen, creating glowing regions of ionized gas. Elsewhere, more ordinary starlight spreads through the galaxy and warms dust grains. Those grains then re-radiate energy in the infrared. Dust can be warmer than the surrounding gas, even though both are tenuous by ordinary standards. In some diffuse interstellar regions, dust temperatures may sit around tens of Kelvin, while gas temperatures differ widely depending on local radiation, density, and recent energetic events. The space between stars is therefore not one calm thermal bath. It is a patchwork in which dust, gas, and radiation each follow their own balance. Supernova explosions add another layer. When massive stars die, they drive shock waves into the surrounding medium. A shock wave is a moving front where gas is suddenly compressed and heated. These explosions stir interstellar space, create expanding shells, and help maintain large volumes of hot ionized gas. Stellar winds from massive stars do something similar on a smaller but still important scale. Over time, these processes make the interstellar medium restless. It is not a still fog between stars. It is a constantly recycled environment shaped by birth, life, and death within the galaxy. This motion matters for cold because it prevents the medium from settling into one simple temperature. Gas cools by emitting radiation, it heats through shocks, ultraviolet light, cosmic rays, and compression. Dust absorbs light and re-radiates it. Magnetic fields and turbulence help guide how structures form and how energy spreads. Turbulence means irregular, chaotic motion across many scales. In interstellar space, it turns the medium into a network of wisps, bubbles, arcs, and diffuse layers rather than a smooth, uniform field. The cold of the region therefore depends on local balance rather than on one universal condition. Even darkness is more complicated here than in intergalactic space. Between stars there may be no nearby sun-like warmth in the ordinary sense, but there is often some background of galactic radiation. Light from many distant stars crosses the medium. Some regions lie exposed to this light, while others are partly shielded by dust and denser gas. Where radiation is stronger, dust and gas respond. Where shielding is greater, cooling can proceed more effectively. Interstellar space is therefore an arena where cold and warmth are continually redistributed by distance, shadow, composition, and motion. The human imagination often treats the space between stars as pure black emptiness. In truth, it is a thin ecology of matter and energy. It is still overwhelmingly sparse, still hostile to ordinary heat transfer, and still governed by vacuum far more than by contact. Yet compared with the larger cosmic regions beyond a galaxy, it is busy. It contains the raw material from which stars form and the remains they return when they die. It carries the marks of stellar radiation, stellar winds, and supernova shocks. Every diffuse cloud and every dust lane alters the local thermal balance. So in the region between stars, the truth about cold space becomes richer and less uniform. Interstellar space is cold because it is thin, because direct thermal contact is weak, and because most of its matter is spread far apart. At the same time, it is never entirely simple. Gas phases span a wide range of temperatures, dust interacts strongly with starlight, and energetic events keep the medium stirred and uneven. Between stars, cold does not mean featureless emptiness. It means a sparse and shifting medium in which heat exists, but never gathers into the dense familiar warmth known on worlds with air, oceans, and solid ground. Deeper inside the interstellar medium there are regions where gas and dust gather closely enough to change the thermal balance in a profound way. These are molecular clouds, broad dark concentrations of matter in which atoms can join into molecules and where outside radiation is partly blocked by the cloud itself. They are still extremely thin compared with any atmosphere or fog on Earth, yet compared with the more diffuse interstellar medium they are dense and sheltered. In these clouds, some of the coldest natural regions in a galaxy begin to appear, not because cold flows in from elsewhere, but because warmth from outside is kept from penetrating very far. A molecular cloud is made mostly of hydrogen, but much of that hydrogen exists in molecular form, with two atoms bound together. Helium is also present, along with many trace molecules and dust grains. Carbon monoxide is especially important in astronomy because it is easier to detect than molecular hydrogen, and often serves as a tracer of the cloud structure. The dust grains, though only a small fraction of the total mass, are crucial. They absorb and scatter visible and ultraviolet light from stars. This shielding protects the inner parts of the cloud from the radiation that would otherwise break apart molecules and raise temperatures more strongly. As a result, the cloud interior becomes dim, chemically rich, and cold. The darkness of these clouds is not merely visual, it is thermal. In more exposed interstellar space, starlight spreads through the gas and dust, heating them to varying degrees. In a molecular cloud, the outer layers intercept much of that energy. Light does not travel freely to the center. The cloud creates its own shadow, and inside that shadow both gas and dust can cool. Dust grains emit infrared radiation, losing energy to space. Gas can also cool through radiation from atoms and molecules under the right conditions. Since external heating is reduced, the balance shifts toward lower temperatures. Many molecular clouds have characteristic temperatures of roughly 10 to 20 Kelvin in their denser interiors, though values vary with local conditions. This is cold in a more intuitive sense than the high temperature yet sparse gas of the galactic halo or hot cavities between stars. In a molecular cloud, the particles are not only sparse on human standards, but also moving more slowly than in warmer phases of the interstellar medium. The dust grains are cold, the gas is cold, the radiation field is weakened. The whole region sits closer to the low radiative background of the galaxy than to the direct heating of nearby stars. This makes molecular clouds some of the best examples of genuine large-scale cold within a galaxy. The cloud is not uniform from edge to center. The outer layers may still receive enough starlight to remain somewhat warmer, while deeper regions cool more effectively. Density also changes from place to place. Some parts are diffuse and extended. Others condense into denser clumps and narrow filaments. A filament is a long thread-like structure of gas and dust. Modern observations show that such filaments are common inside molecular clouds. They are not decorative forms. They are part of the cloud's internal organization, and often the sites where gravity begins to gather matter more strongly. Yet at this stage, the thermal story still centers on shielding. The denser the region, the more effectively it can block radiation and maintain low temperatures. This cold has major chemical consequences. Molecules survive better where harsh ultraviolet light is reduced. Dust surfaces allow atoms to meet and combine. Ices can form on grains in especially shielded regions, adding water, carbon dioxide, ammonia, and other compounds in frozen layers. These processes do not turn the cloud into a solid frozen block. The matter remains overwhelmingly diffuse. But on the scale of interstellar chemistry, low temperature slows some reactions, protects fragile molecules, and makes dust grains important sites for building new compounds. The cold therefore shapes not only temperature, but also composition. Cosmic rays, which are high-energy particles moving through the galaxy, still penetrate molecular clouds to some degree and provide a source of ionization and slight heating. So do occasional nearby stars if the cloud lies in an active region. Turbulent motions also stir the gas. Even in darkness, the cloud is not perfectly still. It shifts, ripples, and fragments over time. Yet these influences usually do not erase the central fact that the interior remains strongly shielded and cold. The cloud is an environment where outside energy loses much of its reach. This makes molecular clouds different from almost every familiar environment on Earth. Earthly cold usually occurs within an atmosphere, where air still transfers heat, and where sunlight can be moderated by weather, surface properties, and circulation. A molecular cloud has no weather in that planetary sense, no breathable air, and no dense medium to carry warmth efficiently from one place to another. Its cold is the cold of radiative isolation. Heat comes in only weakly, escapes by emission and is not rapidly replenished. The result is a quiet, persistent chill on a galactic scale. The visual appearance of such clouds reflects this same physics. In visible light, they often look like dark lanes or blotches against richer star fields because the dust blocks background starlight. In infrared and radio observations, they become more revealing. Astronomers can trace the cold dust by its faint thermal emission and the molecules by their spectral signatures. What seems like an absence in one kind of image becomes a detailed landscape in another. Dense knots, winding filaments, and broad dark interiors emerge from what first appears to be only blackness. That blackness marks regions where light is absorbed, and with that absorption comes shelter from heating. The coldest parts of molecular clouds are especially important because they represent environments where the outward pressure caused by thermal motion is relatively weak. Pressure in gas partly reflects how fast particles move. When temperatures are low, that support is reduced. Gravity then has a greater chance to gather matter into denser pockets. This does not mean every cold cloud collapses at once. Magnetic fields, turbulence, and rotation all matter. But low temperature changes the balance by making it easier for matter to collect rather than disperse. In this way, cold is not only a condition within molecular clouds, it is one of the essential physical ingredients shaping their internal evolution. So in the sheltered depths of interstellar space, cold becomes more direct and more familiar in physical meaning. Molecular clouds are dark because dust blocks light, and they are cold because that same shielding prevents much of the surrounding radiation from reaching their interiors. Dust and gas then radiate energy away and settle toward temperatures of only a few tens of Kelvin. In these quiet regions, the galaxy contains some of its most effective natural cold traps. Places where dimness, chemistry, and thermal balance all combine to produce deep cosmic chill. Far from the inner warmth of the solar system, sunlight begins to lose the authority it has near Earth. The sun remains the central source of nearly all external heating, but with increasing distance its energy spreads over a larger and larger sphere. Each step outward reduces the amount of solar energy falling on a given area. The light is still real and still able to warm matter, but it grows weaker with steady distance. In the outer solar system, cold is no longer an occasional condition shaped by night or shadow. It becomes the dominant background state for worlds, rings, moons, dust, and drifting material. This weakening follows a clear pattern. If a world is twice as far from the sun, the same sunlight is spread over 4 times the area. At Jupiter, the sun is bright but already much less intense than it is at Earth. At Saturn, it is weaker again. By the time sunlight reaches Uranus and Neptune, day is transformed into something far dimmer than the familiar brilliance known on Earth. NASA notes that sunlight at Neptune is about 900 times fainter than at Earth. The sun is still the brightest object in the sky by far, but the energy available for heating has become deeply reduced. The outer solar system therefore provides a natural lesson in radiative balance. A world absorbs some fraction of the sunlight that reaches it and emits thermal radiation back into space. When the incoming and outgoing energy come into balance over time, the object settles around a characteristic temperature, though local details can vary with atmosphere, rotation, composition, and internal heat. As solar input declines outward, those equilibrium temperatures fall. This is why the general trend across the solar system is so simple. The farther from the sun, the colder the average conditions tend to be. That trend does not produce one uniform outer temperature. Jupiter, Saturn, Uranus, Neptune, dwarf planets, and distant bodies beyond Neptune each respond differently. Their sizes, atmospheres, internal heat sources, and reflective surfaces all matter. Yet the broad pattern remains unmistakable. Mean temperatures drop sharply compared with the inner planets. NASA lists average planetary temperatures around -110 degrees Celsius for Jupiter, around -140 degrees Celsius for Saturn, around -195 degrees Celsius for Uranus, and around -200 degrees Celsius for Neptune. Pluto, farther still and much smaller, is colder on average, with NASA listing values near -225 degrees Celsius. These numbers vary depending on how and where temperature is measured, but together they show the same outward decline. The cold of the outer solar system is not caused by some special substance that fills those regions. It is caused mainly by diminished sunlight and by the readiness of objects to radiate their heat away into space. A body far from the Sun receives too little energy to maintain the temperatures common in the inner solar system, unless it has a substantial internal heat source or a strong atmospheric mechanism for trapping warmth. Most of the time, the environment favors cooling. Even so, the outer solar system is not thermally simple. The giant planets complicate the picture because they are not heated only from outside. Jupiter, Saturn, and Neptune all emit more energy than they receive from the Sun. This means they retain significant internal heat from formation and from slow ongoing processes within their deep interiors. Uranus appears more subdued in this respect, with a weaker outward flow of internal energy than the others. Distance from the Sun alone, therefore, does not determine every detail. Yet their upper visible regions and cloud tops still exist under conditions of extreme cold by terrestrial standards. This contrast is important because it shows that cold space does not erase internal history. Giant worlds still release heat left from formation, and that internal energy can drive weather, circulation, and cloud structure even while solar heating is weak. Neptune is a striking case. Though it lies much farther from the Sun than Jupiter, it still shows powerful atmospheric activity. Its clouds and winds are not signs of external warmth. They are signs that internal energy and atmospheric dynamics continue to operate inside a very cold outer environment. Time also changes meaning in the outer solar system. Orbits grow longer, seasons lengthen, and sunlight varies slowly across enormous intervals. Jupiter takes nearly 12 Earth years to circle the Sun. Saturn takes about 29. Uranus takes about 84. Neptune takes about 165. In such distant regions, a seasonal shift can last longer than a human lifetime. This matters for temperature because heating and cooling no longer follow rapid yearly rhythms alone. The emptiness between outer worlds adds to this impression of deep cold. The planets are separated by immense distances. Between them lies the solar wind, magnetic fields, dust, and a very sparse flow of particles from the Sun. The plasma of this environment can have high particle energies, but like other tenuous space environments, it contains too little matter to behave like a warm fluid. Thus, the region remains dominated by weak solar illumination and by radiative loss rather than by direct thermal contact. Beyond Neptune, the solar system continues into the Kuiper belt, where many smaller bodies orbit under still weaker sunlight. This broad zone reinforces the same lesson. The outer reaches of the solar system are not merely farther away in distance, they are farther away in thermal possibility. Energy arrives slowly. Heat escapes readily. The ordinary state of matter there is shaped by persistent cold, long darkness, and the limited power of distant sunlight. So in this region, the truth about cold space becomes closely tied to the fading influence of the Sun. The outer solar system is cold because solar energy weakens steadily with distance, and because worlds radiate away what little heat they absorb. Internal heat can complicate the picture, especially in giant planets, but it does not overturn the larger pattern. Out where sunlight thins across billions of kilometers, cold becomes the default condition, written not by sudden events but by distance itself, and by the quiet efficiency with which the cosmos carries heat away. On many distant bodies in the outer solar system, cold is no longer only a property of the surrounding environment, it is written directly into the ground. Here there are worlds and smaller objects with surfaces made of water ice, nitrogen ice, methane ice, carbon monoxide ice, silicate rock, and darker organic rich material, all lying under weak sunlight and almost no atmospheric protection. These are airless or nearly airless icy surfaces, found on moons, dwarf planets, and countless smaller bodies. They do not hold heat the way an atmosphere holds heat. They do not spread warmth through wind, clouds, or rain. Their temperatures rise and fall mainly by direct sunlight, shadow, and the ability of the surface to absorb and emit radiation. An airless surface behaves very differently from the surface of Earth. On Earth, sunlight warms the ground, but the atmosphere immediately joins the process. Air carries heat away, clouds reflect and trap energy, water stores heat, and weather distributes warmth from place to place. On an icy moon or a dwarf planet with little or no atmosphere, none of that exists in the familiar way. Sunlight strikes the ground directly. The ground absorbs some of that energy depending on its color and texture. At the same time, the surface emits infrared radiation back into space. When sunlight is absent, the surface cools without any blanket of air to slow the loss. This makes temperature change local and immediate. A sunlit slope can become much warmer than a nearby shadowed hollow even when both belong to the same body. A surface facing the sun receives more energy than a surface tilted away. A darker patch absorbs more than a brighter patch. Bright frost reflects much of the incoming light and remains cooler. Darker material, often richer in complex carbon compounds or rocky dust, absorbs more sunlight and warms more readily. On airless, icy worlds, colour is not merely a visual detail, it is a thermal fact. Distance from the sun still sets the larger framework. In the outer solar system, sunlight is weak to begin with. Even at noon on a distant moon, the available solar energy is small compared with the amount falling on Earth. That means the upper limit of daytime warming is low. Nights, meanwhile, can be extremely cold because the surface radiates energy away with little resistance. If a body rotates slowly, the day side may warm for a long time, and the night side may cool for a long time. If it rotates quickly, the temperature contrast can be reduced somewhat because no place spends too long under either condition. Rotation, then, becomes part of the cold. The moon of Earth already provides a simple example of what an airless surface can do. It is not part of the outer solar system, but it shows the same principle clearly. In sunlight, the lunar surface can grow very hot. In darkness, it falls to intense cold. The reason is not mystery. It is the absence of a substantial atmosphere combined with the strong contrast between direct solar heating and free radiative cooling. In the outer solar system, the same logic applies, but under weaker sunlight and across far colder average conditions. Frozen moons and dwarf planets show the same exposed balance with different materials and different distances. Many outer moons are dominated by water ice. Europa, Ganymede, Callisto, Enceladus, Tethys, Dione, Rhea, and many others present surfaces where ice strongly influences reflectivity and thermal behavior. clean water ice reflects a large fraction of sunlight. This high reflectivity is often called albedo, meaning the share of incoming light sent back rather than absorbed. High albedo surfaces tend to remain cooler under the same illumination than darker surfaces do, yet even among icy bodies, surface conditions vary. Dusty contamination, radiation processing, and impacts can darken regions, creating local differences in absorption. A moon is therefore not one temperature spread smoothly over one frozen shell. It is a landscape of cold that changes from place to place. Some bodies carry more volatile ices, meaning substances that freeze and evaporate more easily under outer solar system conditions. Pluto is a well-known example, with surface deposits of nitrogen, methane, and carbon monoxide ice in addition to water ice in harder bedrock-like terrain. These volatile ices migrate over time as seasonal sunlight changes across the body. A slightly warmer region can lose frost to a slightly colder one, which then gains a brighter reflective coating. Surface and temperature influence each other. Warmer areas may darken or lose bright frost. Brighter frosted areas may remain cooler and preserve what they have. In this way, cold is not simply imposed on the surface. The surface responds and reshapes how cold it stays. Permanent shadow creates some of the coldest surface conditions of all. In craters near the poles of certain bodies, the sun may never rise high enough to illuminate the floor. These permanently shadowed regions can remain extraordinarily cold because they lose energy by radiation, but receive almost no direct sunlight in return. On the Moon, such regions preserve water ice. In the outer solar system, where sunlight is already weak, long-lived shadow can deepen cold even further. A little topography can therefore create a sharp thermal boundary between a lit rim and a dark interior. Surface texture also matters. Fine, loose material, often called regolith, heats and cools differently from solid exposed ice or rock. A porous surface may have low thermal inertia, meaning it does not store heat well and responds quickly to changing illumination. Solid or denser material may hold heat a little longer. On an airless, icy world, this can affect the timing and intensity of daily temperature changes. Thermal inertia is a simple idea. It means resistance to temperature change. Where it is low, the ground changes temperature quickly. Where it is higher, the changes are slower. The consequence of all this is that outer icy surfaces are not protected from cold by their own environment. They are directly exposed to the logic of radiation. Sunlight arrives weakly. The surface absorbs part of it. Infrared energy escapes. Shadow removes input. Material properties decide how much is kept and how much is lost. No atmosphere steps in to soften the contrast. This is why a frozen body can show a surface that is both stable over long periods and sharply variable across short distances. So in this region, the truth about cold space becomes visible in the simplest solid form. Airless icy surfaces are cold because they sit under weak distant sunlight, and because they can radiate heat away almost without atmospheric interference. Their temperatures depend on light, shadow, colour, texture, and rotation. On these exposed outer grounds, cold is not hidden in the emptiness between objects. It lies directly on the surface, bright in frost, dark in shadow, and fixed into the frozen face of distant worlds. Closer to the sun, intuition often begins to fail. It seems natural to imagine that space itself must become fiercely hot as one approaches the source of nearly all warmth in the solar system. The sunlight is stronger, the glare is harsher, and the energy arriving on any exposed surface, the sun still remains a vacuum. That fact changes everything. The region is filled with light, with streams of charged particles and with magnetic activity, but it is not filled with dense matter that can surround an object the way hot air surrounds a stone in a desert or steam surrounds metal above boiling water. Near the Sun, there is intense heating by radiation, but empty space itself still does not behave like a hot fluid. This distinction begins with the meaning of vacuum. A vacuum is a region where matter is extremely sparse. In the space near the Sun, sparse does not mean absent. There are particles flowing outward in the solar wind, and in the solar corona, the outer atmosphere of the Sun, there is ionized gas at very high temperature. But even there, density remains extremely low compared with any earthly environment. The particles are far apart. They do not crowd around a surface in the way molecules in air do. They cannot easily transfer heat through ordinary contact at the rate familiar on Earth. So the thermal character of the region is dominated not by immersion in hot material, but by exposure to intense sunlight and to a tenuous plasma. This is why a statement such as the corona reaches temperatures of millions of degrees can be misleading if it is imagined in everyday terms. Temperature here refers to the energy of individual particles. It does not mean the region contains a large amount of heat packed densely enough to roast anything nearby in the way a furnace does. Near the Sun, particle energies can be enormous, but the number of particles in a given volume is still small. An object placed there is affected strongly by radiation from the Sun and also by some interaction with energetic particles. But the surrounding medium does not press against it like a thick hot gas. It is a place of fierce light and low density. Sunlight itself is the main external source of heating in open space near the Sun. The closer an object moves toward the Sun, the more solar energy falls on each square meter of its exposed surface. If that surface absorbs much of the light, its temperature rises until the energy it emits back into space balances what it gains. This is radiative balance. The object does not become warm because space around it has turned into hot air. It becomes warm because sunlight pours directly onto it, and because the object can only lose that energy by re-radiating it. Shade therefore becomes decisive. A surface facing the Sun may heat intensely, while a shaded surface nearby can remain far cooler. This sharp dependence on exposure is one of the clearest signs that empty space near the Sun is not hot in the ordinary atmospheric sense. In air, heat spreads by convection, meaning warm fluid rises and carries energy with it, and by conduction, meaning particles collide and pass energy from place to place. In open space, those pathways largely vanish outside the object itself. A spacecraft can therefore experience severe thermal contrast between one side and another. The side in sunlight may become extremely hot. The side in shade may radiate energy away and remain comparatively cold. Near the Sun, heat is not shared evenly by a surrounding medium. It is imposed directionally by radiation. The Parker Solar Probe provides a practical demonstration of this truth. It travels closer to the Sun than any previous spacecraft and passes through parts of the corona where the particle temperature is extraordinarily high. Yet the spacecraft does not simply melt because the corona is so tenuous. Its heat shield faces the Sun and is designed to absorb and re-radiate intense solar energy while keeping the instruments behind it in deep shade. The shield itself becomes extremely hot, but the protected interior remains much cooler. This difference shows that near solar space is not a bath of dense heat. It is an environment where geometry, exposure, and surface properties determine survival. Surface properties matter because not all materials interact with sunlight in the same way. A bright reflective surface sends more solar energy away and absorbs less. A dark surface absorbs more and heats more strongly. A material that emits infrared radiation efficiently can shed absorbed energy more effectively than one that traps it. Engineers designed spacecraft for the inner solar system by controlling these properties very carefully. Coatings, multi-layer insulation, radiators, and shields all exist because in vacuum there is no air to moderate temperature. The balance is set by light absorbed, heat generated internally, heat conducted through the craft, and radiation emitted back into space. Even very close to the Sun, open space can therefore contain both extreme heat and sharp cold at once, depending on direction and exposure. A sunlit surface can rise to temperatures that damage or destroy ordinary materials. A shaded component can remain much cooler if it is isolated from that sunlight and allowed to radiate away its energy. The absence of a thick surrounding medium allows this contrast to persist. Near the Sun, light is intense, but emptiness remains emptiness. The solar wind adds another layer to the environment. It is a continuous outward flow of charged particles from the Sun, carrying energy, momentum, and magnetic structure through the solar system. These particles matter for electronics, radiation exposure, and space weather. They also interact with spacecraft surfaces, yet the solar wind does not change the central thermal rule of open space. It remains too thin to behave like a dense hot wind on Earth. Its particles are energetic, but they do not transfer heat in the same familiar continuous way as air across a surface. The thermal problem near the Sun is therefore still dominated by radiation. This helps explain why simple language often causes confusion. To say that space near the Sun is hot is partly true if the meaning is that intense sunlight can heat exposed objects to very high temperatures. It is not true if the meaning is that empty space itself has become a dense hot substance. The vacuum remains a vacuum. The corona can have extremely high particle temperatures, but low density. Sunlight can be overpowering, but only where it strikes. Shade can still preserve cold. These are not contradictions. They are the natural consequences of radiative heating in a sparse environment. So in the open space near the Sun, the truth about cold becomes unusually precise. Space does not stop being a vacuum merely because the Sun is near. It fills with stronger radiation, more energetic particles, and more severe thermal contrast, but it still lacks the dense matter required for ordinary atmospheric warmth. Near the Sun, an object heats because it absorbs sunlight, and cools because it emits radiation. What matters is exposure, shadow, material, and orientation. The emptiness itself does not become hot the way heated air becomes hot. Even under the strongest solar glare, space remains what it is: bright, sparse, and thermally governed by radiation alone. Around Earth, space appears close, familiar, and almost domestic compared with the deeper reaches of the solar system. Yet the thermal reality of orbit remains severe. Near Earth, cold and heat alternate not because the surrounding vacuum changes its nature, but because objects move repeatedly between direct sunlight and shadow, while also receiving light reflected from Earth and infrared radiation emitted by Earth itself. In this region, the truth about cold space becomes a matter of cycling exposure. The environment is not defined by one stable temperature. It is defined by contrast. Low Earth orbit is the clearest example. A spacecraft there circles Earth in roughly 90 minutes. During each orbit, it can pass from brilliant sunlight into darkness, and then back into sunlight again. There is no thick surrounding air to smooth these changes. A surface facing the Sun absorbs strong solar energy. A surface turned away from the Sun can cool by radiating heat into space. When Earth blocks the Sun, direct solar heating drops sharply, and shadow takes over. This produces a repeated thermal rhythm unlike anything on the surface below. Earth itself modifies the balance in two important ways. First, it reflects sunlight, clouds, oceans, deserts, ice, and the atmosphere send part of the incoming solar energy back into space. This reflected light is often called albedo, meaning the fraction of light returned rather than absorbed. A spacecraft in orbit can receive this reflected brightness from the side facing Earth. The amount depends on what lies below. Bright cloud tops and ice-covered regions reflect more than darker ocean or forest. Second, Earth emits infrared radiation because Earth is warm. This outward thermal glow provides an additional source of energy to objects in orbit, especially to surfaces that face the planet. So near Earth, a spacecraft does not interact only with the Sun and with deep space. It also interacts constantly with the planet beneath it. This makes orbital temperature more complicated than a simple day and night cycle. In full sunlight, a spacecraft may receive direct solar heating, reflected sunlight from Earth, and infrared radiation from Earth all at once. In eclipse, meaning the period when Earth blocks direct sunlight, the spacecraft still receives Earth's infrared glow and sometimes reflected light from the atmosphere or upper cloud layers near the boundary of shadow, though much less than in full daylight. At the same time, every exposed surface continues emitting its own infrared radiation away into space. The actual temperature reached by a surface depends on its orientation, material, color, and connection to the rest of the spacecraft. A white-painted surface and a black surface behave differently. A bright surface reflects more sunlight and often stays cooler under illumination. A dark surface absorbs more and warms more strongly. A polished metal surface may reflect well in visible light, but emit infrared less efficiently than a coated radiator designed to shed heat. Engineers therefore choose exterior materials with great care. Thermal control in orbit is not an optional refinement. It is necessary for survival of electronics, batteries, fuel lines, sensors, and living spaces. The International Space Station shows this clearly. It orbits close enough to Earth to experience repeated passes through sunlight and darkness many times each day. Its large solar arrays, radiators, modules, and truss structures all encounter different thermal conditions depending on angle and exposure. Parts in direct sunlight can become very hot. Parts in shadow can become very cold. Internal systems must keep laboratories, equipment, and crew spaces within a narrow range suitable for operation and life. This is achieved not because near-Earth space is gentle, but because the station actively manages severe thermal swings. The vacuum remains central to this problem. In orbit, there is still too little matter for ordinary convection, meaning there is no surrounding air to carry heat evenly across surfaces. Conduction occurs only within connected materials, such as metal frames, panels, pipes, or insulation layers. Radiation becomes the main way a spacecraft exchanges heat with its surroundings. This is why spacecraft often include radiators, reflective blankets, and carefully placed insulation. Heat must be moved internally toward regions where it can be emitted or blocked from entering in the first place. Near Earth, the challenge is not merely cold. It is alternating cold and heat without any atmospheric cushion between them. Even a human body in orbit encounters this principle through spacesuit design. Outside a spacecraft, the body cannot rely on air to remove excess heat or supply warmth. A suit must provide insulation, reflective protection, and internal temperature control. In sunlight, the outer layers may absorb strong energy. In shadow, the suit may lose heat by radiation. Life support systems regulate this balance continuously. The presence of Earth nearby does not make open orbital space comfortable. It only adds another strong source of radiation to be managed. Altitude also matters. In very low orbit, there remains a trace of upper atmosphere, enough to cause drag over time but still far too thin to act as a normal thermal medium. Farther out, the atmosphere becomes even less relevant. Yet whether in lower or somewhat higher orbit, the basic thermal rule persists. Direct sunlight warms, shadow cools, Earth reflects and emits. The object's own design determines how those influences combine. Rotation and motion within the spacecraft change the picture further. A slowly rotating surface can spend more time heating or cooling. A tumbling object may distribute sunlight over more areas and avoid prolonged overheating of one side. Though uncontrolled tumbling can create other problems. Large spacecraft with many connected parts also develop internal thermal gradients. One side of a panel may face the sun while the other faces dark space. One section may radiate heat efficiently, while another traps it. In orbit around Earth, temperature is therefore not one condition spread across a vehicle. It is a map of local balances constantly changing with position and attitude. This region also teaches an important lesson about the meaning of cold. Near Earth, the background of space remains cold, and surfaces in darkness can lose heat quickly by radiation. But the same orbit can also expose these surfaces to intense heating moments later. Cold is real, yet it is not solitary. It exists beside strong warmth, with the vacuum allowing both extremes to remain close together rather than blending into a mild average. The result is an environment of sharp thermal contrast, not a single frozen state. So around Earth, the truth about cold space becomes dynamic and rhythmic. Orbital space is cold because it remains a vacuum in which shaded objects radiate heat away efficiently. It is also thermally harsh because sunlight arrives directly and strongly, while Earth adds reflected light and infrared glow from below. A spacecraft in this region lives between brightness and shadow, not inside one stable temperature field. Near Earth, cold is not absent, but it is inseparable from heat, and both are governed by exposure, motion, and the persistent emptiness of space. At the edge of a planet's gaseous envelope, there is a region where atmosphere does not end suddenly, but becomes thinner and thinner until it merges with space. This outermost realm is often called the exosphere. Below it, on planets with an atmosphere like Earth, lies the thermosphere, a region where individual particles can carry considerable energy, while the gas as a whole remains extraordinarily tenuous. These layers are important because they show how the ordinary idea of temperature begins to break apart when matter becomes too sparse for warmth to behave in familiar ways. Here, high particle energy and weak total heat exist side by side. An atmosphere near the ground feels continuous. Air surrounds every surface, presses on every object, and transfers heat readily through collisions. In the exosphere, that sense of atmosphere almost disappears. The gas is still there, but the particles are so far apart that one particle can travel a long distance before colliding with another. The region does not behave like a wind-filled sky. It behaves more like a gradual fading of atmosphere into vacuum. Matter remains present, but only in trace amounts. The thinness becomes the main physical fact. This has strong consequences for temperature. In dense gas, temperature usually tracks everyday experience reasonably well. If air is hot, it quickly warms what it touches. If air is cold, it draws heat away. In the thermosphere and exosphere, particles can move with great energy, especially when they absorb ultraviolet light and X-rays from the sun. Technically, This corresponds to very high temperatures. In Earth's thermosphere, for example, particle temperatures can rise to hundreds or even more than 1000 degrees Celsius depending on solar activity. Yet an object there does not feel surrounded by a furnace. The number of particles is too small to transfer much total energy by contact. The gas is hot in the language of particle motion, but weak in the language of total heating. This distinction becomes clearer when density is considered. Near Earth's surface, even cool air contains an enormous number of molecules in every small volume. Those molecules strike a surface constantly, exchanging energy rapidly. In the uppermost atmosphere, the particles are few. Each one may carry significant energy, but there are too few impacts to produce the same warming effect. A surface exposed in low Earth orbit is influenced far more by sunlight, Earth's infrared radiation, and its own thermal emission than by direct heating from the thin upper atmosphere around it. The atmosphere is present, but it has lost the dense collective power associated with ordinary air. The exosphere is therefore not best imagined as a boundary line but as a fading region. On Earth it begins above the denser layers and extends outward where hydrogen, helium, and a few heavier particles can follow long paths under gravity, sometimes even escaping into space. Escape becomes possible because the particles in these upper layers are not tightly confined by frequent collisions. If one moves fast enough in the right direction, it may never return. This is another sign of how thin the region is. A dense atmosphere mixes and holds itself together through constant interaction. The exosphere is so diffuse that individual particle paths begin to matter. Other worlds show similar principles in different forms. Mercury has only an extremely tenuous exosphere, produced in part by particles knocked off its surface by sunlight, solar wind, and tiny impacts. The Moon also has a very thin exosphere, so sparse that it is often described as a surface-bounded exosphere, meaning particles spend much of their time travelling between the ground and space, rather than behaving like a normal atmospheric gas. Mars has a much thinner atmosphere than Earth overall, and its upper layers also grade outward into a very sparse exosphere. In each case, the lesson is the same. A planet or moon can retain a trace outer envelope of particles without possessing anything like a thick heat-sharing atmosphere. Solar radiation is central in these regions because there are so few other strong energy pathways. Ultraviolet light and X-rays from the sun are absorbed by atoms and molecules in the upper atmosphere, increasing their energy and often ionizing them. Ionization means electrons are removed from atoms or molecules, creating charged particles. This process contributes to the ionosphere, an electrically active region that overlaps part of the upper atmosphere. Yet even here, where solar input directly energizes matter, the thinness of the gas prevents the formation of familiar warmth. The particles become fast. The region does not become comfortable or furnace-like. The total thermal content per volume remains very low. Earth's auroras reveal another aspect of this thin upper realm. Charged particles guided by Earth's magnetic field enter the upper atmosphere and transfer energy to atoms and molecules, causing them to emit light. The colours appear in a region that is both active and sparse. The same environment can be electrically dramatic, chemically reactive, and technically very hot while remaining far too thin to warm objects in the way dense air would. This combination often seems strange only because daily human experience is confined to dense layers much lower down. Even drag in low Earth orbit reflects this reality. A spacecraft moving through the upper atmosphere encounters enough particles to feel resistance over time, especially in lower orbits. That drag can gradually reduce altitude, yet the gas causing it is still far too tenuous to act like normal wind. Its effect appears across long durations rather than through a strong immediate push. When solar activity increases, the upper atmosphere expands, density at a given altitude rises, and drag becomes stronger. This shows that the region, though thin, remains responsive to solar heating and still has measurable consequences for orbiting objects. Thermal behavior in thin atmospheres is therefore a matter of limited contact. A particle can be energetic. A region can have a high defined temperature, but if very few particles strike a surface, the total heat transfer remains small. This is why the thermosphere and exosphere stand as important examples in the study of space cold. They sit between ordinary atmosphere and open vacuum, revealing how temperature alone cannot describe what warmth or cold actually does. So in these uppermost atmospheric regions, the truth about cold space becomes more exact. Thin atmospheres and exospheres can contain particles moving with enough energy to correspond to very high temperatures, yet the regions still hold little total heat because matter is so sparse. The atmosphere fades into space not by turning sharply off, but by becoming too thin to behave like air at all. In that fading warmth loses its familiar meaning, and cold reappears not as the absence of energy in every particle, but as the absence of enough particles to make that energy count in ordinary ways. To understand how cold space really is, it becomes necessary to pause at the level of principle and consider what heat means when almost all matter is gone. In ordinary life, warmth and cold are usually felt through contact with air, water, cloth, stone, or metal. A hand touches a surface. Wind passes over skin. Water draws heat from the body or gives it back. These experiences depend on matter being close enough and dense enough to exchange energy rapidly. In space, that familiar framework falls away. The vacuum does not remove heat by touch, because the vacuum has almost nothing in it to touch with. This is why the idea of cold in space must be understood through the ways heat actually moves. Heat is energy in transfer. It flows from a place or object at higher temperature to one at lower temperature. There are three main ways this happens. Conduction is the transfer of heat through direct contact, as when one end of a metal rod becomes warm and the heat passes through the rod to the other end. Convection is the transfer of heat by the bulk movement of a fluid, such as air or water, as when warm air rises and cool air sinks. Radiation is the transfer of energy by electromagnetic waves, which can travel through empty space. On Earth, all three often operate together. In space, radiation dominates, while conduction and convection become limited or vanish outside connected materials. This is one of the most important differences between the cold of space and the cold of Earth. On Earth, cold air can move around a body and pull heat away continuously. That is convection. Clothing works partly because it traps air and slows that process. In water, heat leaves the body much faster because water is denser and carries energy away more effectively than air. In vacuum, there is no such surrounding fluid. A human body, a spacecraft panel, or a stone does not lose heat because cold emptiness is flowing over it. It loses heat mainly by radiating infrared energy outward. This can seem surprising because vacuum is often described as extremely cold. The statement is useful in a broad sense, but it must be understood carefully. A vacuum is not cold in the way ice is cold or winter wind is cold. Ice and wind are made of matter. They can take heat directly through contact and movement. Vacuum is mostly absence. It does not have dense particles available to carry heat away by collision. So an object in vacuum does not instantly freeze just because it is surrounded by emptiness. What happens instead depends on the object's balance between the radiation it absorbs and the radiation it emits. If an object in space receives no substantial incoming radiation, then it gradually cools by emitting its own thermal radiation. Every object above absolute zero emits electromagnetic energy, mainly in the infrared if its temperature is moderate. As it radiates, it loses energy and its temperature falls. This cooling continues until it reaches balance with whatever radiation field remains around it. In deep space, far from stars and planets, that background is very faint, so objects can become very cold over time. But the process is not immediate. It depends on surface area, material properties, orientation, and internal heat content. Conduction still exists in space, but only within matter itself or between objects that touch. If one part of a spacecraft is heated by sunlight, heat can conduct through the structure into cooler parts. A metal frame can spread energy from one panel to another. A cable, pipe, or bolt can do the same on a smaller scale. This internal conduction matters greatly in engineering because it helps determine whether sensitive components overheat or remain stable. But the conduction occurs inside the object, not through the surrounding vacuum. Space does not conduct heat to or from the object in the ordinary way because the necessary dense medium is missing. Convection, by contrast, is almost entirely absent in open space. Convection requires a fluid, usually a gas or liquid, that can move and carry heat with it. In the cabins of spacecraft and space stations, air circulation must be actively managed because natural convection becomes weak or behaves differently in microgravity. Warm air does not rise in the same ordinary way when weight and buoyancy lose much of their usual effect. Outside the spacecraft there is no usable fluid at all. This means one of the most familiar heat transfer processes in daily life disappears almost completely once the atmosphere is left behind. Radiation therefore becomes the master process. Sunlight warms a surface because the surface absorbs part of the incoming electromagnetic energy. A shaded surface cools because it continues to emit radiation without receiving as much in return. A planet can warm a nearby spacecraft by reflecting sunlight or by emitting infrared radiation. Deep space can remain a sink for emitted heat because it offers so little incoming energy in compensation. The entire thermal life of an object in space becomes a problem of radiative balance. This also clarifies the meaning of temperature in a sparse environment. Temperature is related to the average energy of motion in particles, but heat transfer depends not only on that average energy, but also on how many particles are present and how often they interact. A very thin gas can have energetic particles and yet transfer little total heat. A dense gas at a lower temperature can transfer heat much more effectively because there are so many more collisions. This is why the vacuum of space, or the thin gas in upper atmospheres and solar plasma, does not behave the way the raw temperature number might suggest. Human intuition often expects cold to be aggressive, as if space should reach out and seize heat at once. In reality, the vacuum is passive. It permits heat to leave by radiation. But it does not actively strip energy by contact the way cold water does. This is why thermal protection in space focuses so much on controlling radiation. Reflective surfaces reduce absorption. Insulation reduces internal conduction between hot and cold parts. Radiators increase controlled emission where excess heat must be discarded. Shadow shields sensitive equipment from direct sunlight. Every solution follows from the same truth in vacuum. Heat transfer is no longer shared among the familiar earthly pathways. So in this region of pure principle, the truth about cold space becomes especially clear. Space is cold not because emptiness itself behaves like frozen matter, but because in vacuum the usual ways heat moves are largely removed. Conduction survives only within touching materials. Convection disappears without a dense fluid. Radiation remains, and through radiation an object gains or loses energy. The cold of space is therefore a radiative condition, not a windy one, not a fluid one, and not a solid one. Once that is understood, the strange thermal logic of the cosmos becomes much easier to see. Once the environment of vacuum and radiative heat transfer is understood, the next inward region lies on the surface of the object itself. In space, a body does not simply inherit one temperature from its surroundings. Its thermal state depends on how it meets radiation. Light arrives. Some is reflected, some is absorbed, and energy already inside the object is emitted away again. The balance between those processes determines whether the object warms, cools, or remains near a steady level. This means that in space, cold is not only a property of place, it is also a property of how a surface behaves. Color is one of the simplest parts of this behavior, but it is not the whole story. A bright white surface usually reflects a large fraction of visible sunlight and absorbs less of it. A dark surface usually absorbs more and reflects less. Under the same sunlight, the darker surface tends to warm more strongly. This principle is familiar on Earth in simple ways, such as the difference between light and dark clothing under a hot sky. In space, the same logic becomes more direct because there is no air to soften or spread the effect. What the surface absorbs matters immediately, yet visible color alone does not decide everything. A surface must also emit energy. The ability of a material to emit thermal radiation is often called emissivity. In simple terms, this means how effectively a surface gives its heat away as infrared radiation. Some surfaces absorb little sunlight and also emit heat well. Others reflect strongly in visible light but are less efficient at shedding infrared energy. Because of this, two objects with similar appearance to the eye can behave differently in space. Their temperature depends not only on how much light they take in, but also on how readily they let energy go. Texture matters as well. A polished smooth surface and a rough matte surface do not interact with light in the same way. Smooth reflective materials can send a large share of incoming radiation away in preferred directions. Rougher surfaces tend to scatter light more diffusely, with more opportunity for absorption. At the same time, texture affects how a surface re-radiates heat and how it stores energy in its outer layers. In vacuum, where radiation rules, even small differences in finish can lead to meaningful differences in thermal behavior over time. Orientation is equally important. A flat panel pointed directly at the sun receives more solar energy per unit area than one tilted at a steep angle. If the panel turns edge onto the sun, the incoming energy falls sharply. The same object can therefore be hot in one position and much cooler in another, without any change in distance from the sun. Spacecraft designers use this fact constantly. By changing attitude, meaning the direction a craft faces, they can limit heating, protect sensitive instruments, or help radiators point toward cold, dark space where they can release energy more efficiently. Shape adds another layer. A sphere shares incoming light across a curved surface, while a flat plate presents one face strongly to the sun and leaves the other in shade. A deep recess or cavity can trap radiation more effectively than an open exposed plane. Edges, corners, and layered structures produce local hot and cold regions because each part sees the sun, the planet nearby, and deep space in different proportions. An object in space, therefore, does not usually have one neat overall temperature. It develops a thermal geography across its own body. Rotation changes this geography over time. A slowly rotating object may leave one side exposed to sunlight long enough for substantial warming, while the opposite side remains in extended darkness and cools deeply. A more rapidly rotating object spreads sunlight over a broader area and reduces the time any one point spends under direct heating. This can soften temperature extremes, though it does not remove them entirely. The familiar daily cycle on a planet is one example of this principle, but in space it applies to any rotating body, from a small asteroid to a spacecraft or moon. Rotation is therefore a thermal moderator, not because it creates heat, but because it redistributes exposure. The ability of a material to store heat also matters. This property is often called thermal inertia, meaning resistance to rapid temperature change. A surface with low thermal inertia warms quickly in sunlight and cools quickly in darkness. A surface with higher thermal inertia changes more slowly because it stores more energy, relative to the rate at which radiation adds or removes it. Fine dust often has lower thermal inertia than solid rock. Thin metal parts may change temperature quickly, while larger connected masses respond more slowly. In space, this determines whether a body swings sharply between heat and cold or passes through a gentler cycle. Nearby sources of radiation complicate the balance further. An object near Earth receives not only sunlight, but also reflected light and Earth's infrared emission. An object near a bright moon, a ring system, or a large spacecraft can exchange radiation with those surfaces as well. Even deep space is not a perfect absence, because the cosmic microwave background still exists and distant stars add faint contributions. Yet in most practical solar system situations, the dominant terms remain sunlight absorbed and thermal radiation emitted. The surface lives between those two streams. This is why two objects sitting side by side in space can reach different temperatures. One may be coated in bright reflective material and remain relatively cool. The other may be darker, absorb more sunlight, and become much warmer. One may radiate heat efficiently and settle into balance quickly. Another may hold heat longer and stay warm after exposure ends. One may rotate and distribute the load. Another may remain fixed and suffer greater extremes. Space does not impose a single temperature equally on all things. Each surface negotiates its own balance through its material and its orientation. This principle explains many otherwise surprising cases. A bright, icy surface far from the sun can remain extremely cold because it absorbs little of the weak light it receives and emits its stored heat readily. A dark asteroid somewhat closer to the sun may grow much warmer in daylight. A spacecraft instrument hidden behind a sunshield may stay cold, even while nearby panels in direct sunlight grow hot. In every case, the surrounding vacuum allows the contrast to persist because there is no dense medium to average everything together. So in this region, the truth about cold space rests on the meeting between radiation and material. Light, surface finish, color, shape, rotation, and heat storage all determine whether an object in space warms or cools. Cold is not delivered equally by emptiness. It emerges from balance. A surface absorbs energy according to what it faces and what it is made of, and it loses energy according to how well it radiates. In the vacuum of space, that balance becomes the decisive law written directly on every exposed object. Once radiation, surfaces, and thermal balance are understood, the next inward region is not a place in nature, but a human response to nature. Spacecraft, instruments, and spacesuits are built to survive an environment in which empty space does not protect against heat and does not protect against cold. In vacuum, sunlight can raise the temperature of an exposed surface sharply, while darkness can allow heat to drain away by radiation. because there is no surrounding air to soften these changes. Every working machine and every protected human body in space must carry its own thermal strategy. Survival depends on control. A spacecraft is never simply placed into space and left to accept whatever temperature comes. Its structure is designed as a system for managing energy. Some heat arrives from the sun. Some comes from a nearby planet through reflected light and infrared emission. Some is generated inside the craft by electronics, batteries, motors, pumps, computers, and scientific instruments. All of this heat must be directed, limited, stored, or released. If a spacecraft grows too hot, components may fail and materials may distort. If it grows too cold, batteries may weaken, lubricants may thicken, fuel lines may freeze, and delicate instruments may stop working accurately. Thermal control is therefore one of the central conditions of spaceflight. The first line of protection is often passive control, meaning protection that works through design rather than through moving machinery. Shape, orientation, surface coatings, insulation, and sun shields all belong to this category. A spacecraft can be covered in reflective materials that reduce solar absorption. It can place vulnerable instruments behind protective structures that block direct sunlight. It can use multi-layer insulation, a blanket built from many thin reflective sheets separated by small gaps to slow the unwanted movement of heat between the spacecraft and its surroundings, or between one internal part and another. These blankets are common on satellites and probes because in vacuum radiation is the main external pathway for heat exchange. Sun shields are among the clearest examples of thermal design. A sun shield is a carefully engineered barrier that absorbs, reflects, and re-radiates incoming energy in controlled ways. By keeping one side toward the sun and the protected side in permanent shade, a spacecraft can create two very different thermal zones within a short distance. The James Webb Space Telescope shows this principle dramatically. Its layered sunshield allows the telescope and its infrared instruments to remain extremely cold, while the sun-facing side encounters far greater heating. This separation is essential because infrared astronomy depends on detecting faint heat from distant objects, and a warm telescope would overwhelm its own observations. Other spacecraft rely heavily on radiators. A radiator is a surface designed to emit heat efficiently into space. Inside a spacecraft, electronics and life support systems generate waste heat. Without air or water outside to carry that heat away, it must be moved by conduction and fluid loops to panels that face cold space and radiate it outward. Radiators therefore work as controlled windows through which excess internal energy escapes. They are often placed where they avoid direct sunlight and strong thermal input from a nearby planet. Active thermal control adds another layer. This means systems that use pumps, heaters, thermostats, or circulating fluids to adjust temperatures as conditions change. A probe traveling from the inner solar system to the outer regions may face very different thermal environments over its mission. Instruments may need narrow temperature limits regardless of whether the craft is in sunlight, eclipse, or deep cruise. Heaters can protect tanks, valves, and electronics from falling below safe limits. Fluid loops can move excess warmth from crowded internal compartments to radiators. Through such systems, a spacecraft becomes thermally active rather than merely insulated. Human protection follows the same logic but under stricter limits. A human body generates heat continuously through metabolism and must remain within a narrow internal temperature range. In open space, the body cannot rely on air to remove extra heat or to slow cooling. A spacesuit must therefore act as a small independent environment. Its outer layers reflect sunlight, resist damage, and reduce radiative exchange. Beneath them are pressure layers, structural layers, and systems that help regulate temperature. One of the most important parts is the liquid cooling and ventilation garment worn inside the suit. Water flows through fine tubes near the body and carries excess heat away, while ventilation helps manage moisture and gas circulation. The removed heat is then rejected through the suit's life support system. This arrangement reveals an important truth. In space, overheating can be as serious a threat as freezing. A suited astronaut in sunlight, working hard, generates internal heat and also absorbs external radiation. Without active cooling, that heat could build dangerously. In shadow, by contrast, heat loss by radiation can become a greater concern. The suit must therefore manage both directions at once. It cannot simply insulate, it must regulate. Crewed spacecraft extend this principle to the whole cabin. Inside, equipment, lights, computers, and human bodies all generate heat. In microgravity, natural convection is weak, so fans circulate air to prevent pockets of warmth, carbon dioxide buildup, and condensation. Internal heat is collected and carried to radiators or other control systems. The cabin itself is wrapped and coated to reduce unwanted gain or loss through the hull. Even within a pressurized spacecraft, thermal control remains a constant engineered balance rather than a passive consequence of being enclosed. Scientific instruments often impose the most demanding requirements. Some detectors must be kept cold to reduce internal noise. Infrared instruments are especially sensitive because warmth within the instrument itself can mask the faint signals they are meant to measure. This is why some observatories use cryo-coolers or large sunshields to achieve very low operating temperatures. Other instruments must not become too cold because their electronics or moving parts depend on stable moderate warmth. A single spacecraft can therefore carry devices that need different thermal zones, each carefully maintained within its own limits. So in this region, the truth about cold space becomes a matter of engineering and survival. Spacecraft and suits endure because they control radiation, guide internal heat, create shade, reject excess warmth, and defend vulnerable systems against deep cooling. Vacuum offers no gentle middle ground. It forces design to be deliberate. Every reflective coating, every insulated blanket, every radiator panel, every heater, and every cooling loop is an answer to the same condition in space. Heat does not behave kindly or evenly, and protection depends on understanding that fact in detail. After the scale of galaxies, voids, planetary surfaces, vacuum, light, and machines, the final inward region lies inside matter itself. Here the cold of space reaches its most basic meaning. Cold is not ultimately a property of darkness or distance alone. It is a condition of motion within matter. Atoms vibrate in solids, molecules rotate, vibrate, and travel through gases and liquids. Electrons occupy allowed energy states. When a material is warm, many of these motions and excitations are more energetic on average. When a material is cold, they are less energetic on average. Space matters because it can allow energy to leave, but the actual state called cold exists inside the particles and structures of matter. Temperature is the measure that connects this inner world to the larger universe. In simple terms, temperature describes the average energy associated with random motion in a material. In a gas, that means the wandering movement of particles through space. In a solid, it means the vibrations of atoms around their positions in a lattice, which is an ordered arrangement of atoms. In a liquid, it includes both motion and changing local structure. The exact microscopic details differ, but the broad idea remains the same. Higher temperature means greater average microscopic agitation. Lower temperature means less. This is why the cold of space does not act directly as a substance. Instead, a material exposed to a cold radiative environment loses energy, and the particles inside it settle into lower energy patterns. A metal panel in shadow emits infrared radiation. As it loses that energy, the atoms of the metal vibrate less strongly. A grain of dust in a dark molecular cloud radiates its heat and cools until its internal motions match a lower thermal balance. Frozen nitrogen on a distant dwarf planet remains solid because the particles inside it do not carry enough energy to move freely past one another as a liquid would under those conditions. In every case, cold is expressed as a reduction in microscopic activity, even in solids that appear still. This hidden motion never disappears entirely. Atoms in a crystal are not motionless points. They vibrate continually. The vibration may be small, but it remains real. At lower temperatures, the vibrations become weaker. The solid often contracts slightly because the average spacing between atoms decreases as thermal motion declines. This is why many materials shrink when cooled. It is not because cold compresses them from outside like a hand closing around an object. It is because the internal jostling that keeps atoms slightly farther apart becomes less vigorous. Gases show the same principle more openly. A gas is warm when its particles move rapidly in many directions, colliding and exchanging energy. It becomes cooler when that average motion slows. Pressure may also fall if the gas is allowed to spread or if energy escapes. In space, this matters for every thin atmosphere, every cloud, and every stream of plasma. The vast scale of the cosmos may seem remote from the microscopic level, but the connection is direct. When astronomers speak of gas at 10 Kelvin or 1,000,000 Kelvin, they are describing the energy of the particle motions inside that gas, even if the density is so low that the region still feels empty in practical terms. Molecules add further structure to the meaning of temperature because they can store energy in several ways. They can move from place to place, rotate, and vibrate internally. At higher temperatures, more of these modes are excited. At lower temperatures, fewer are significantly occupied. This affects chemistry, infrared emission, and the formation of solids and ices. In very cold environments, some molecular motions become less active, and molecules may cling to dust grains or to one another more easily. This is one reason cold regions of space can preserve ices and fragile compounds that would not survive in warmer surroundings. The microscopic energy budget shapes the visible state of matter. The Kelvin scale is especially useful here because it begins at absolute zero, the theoretical lower limit of temperature. Absolute zero does not mean ordinary emptiness. It means the lowest limit of thermal energy allowed by the laws of physics. A classical picture might suggest that all motion stops there. But quantum physics gives a more careful answer. Even at the lowest possible temperature, particles in bound systems retain a minimum residual motion called zero-point energy. This is a consequence of the uncertainty principle, which prevents position and momentum from both being fixed exactly. Matter can become extraordinarily cold, but not perfectly still in the simple mechanical sense. This quantum truth makes the deepest cold of nature more subtle. A material cooled toward absolute zero does not become a dead frozen geometry without any internal life. Instead, many thermal motions are suppressed while certain minimum fluctuations remain. Under laboratory conditions, matter can be cooled to tiny fractions of a Kelvin above absolute zero, and strange quantum behaviors can become easier to observe. In the natural cosmos, Such extreme artificial cooling is rare, but the principle still matters because it shows that cold is not mere absence. It is a state constrained by deep physical rules. Cold also changes the collective behavior of materials. Electrical resistance in some substances decreases as temperature falls, and in certain materials it can vanish in the state called superconductivity. Heat capacity, meaning the amount of energy needed to change temperature, also changes with temperature. Mechanical strength, brittleness, magnetic order, and chemical rates can all shift as internal motions decline. The microscopic state therefore governs not only how cold matter is, but what matter does while cold. A spacecraft material in shadow, an ice grain in a comet, and a sensor cooled for astronomy all respond according to the same basic truth: lower thermal motion changes physical behavior. This inner view also resolves a final misconception. Space is often imagined as cold because it is dark and far from warmth, as though cold were a background mood of emptiness. Darkness and distance matter, but only because they influence energy exchange. The real condition of cold is inside matter. If radiation leaves faster than it arrives, internal energy falls. If internal energy falls, atomic and molecular motions decrease. If those motions decrease, the material becomes colder. The grandest cosmic scenes and the smallest microscopic ones are therefore connected without any break in logic. The cold between galaxies, the chill of a shaded crater, and the cooling of a spacecraft panel all meet at the same physical level inside atoms and molecules. So in the final inward region, the truth about how cold space really is becomes exact. Space provides the environment in which energy can be lost, but cold itself is the lowering of microscopic motion within matter. Atoms vibrate less. Molecules move and rotate less energetically. Solids contract. Gases slow. Chemistry changes, and materials behave differently because their internal energy has fallen. The vast cold of the cosmos is therefore not separate from the small hidden life of matter. It is expressed there, in the quieting motions of particles, where the largest emptiness in the universe reaches the smallest scales of existence. Cold in space is not a simple opposite of warmth. It is the long quiet result of distance, thinness, shadow, and release. Across the universe, energy spreads, fades, and leaves matter to settle into lower states of motion. The background glow of the cosmos remains faint. The spaces between galaxies remain sparse. Clouds keep their darkness by blocking light. Distant surfaces hold frost because weak sunlight cannot easily replace what radiation carries away. Near the sun, even brilliance does not change the emptiness into hot air. Around Earth, heat and cold pass each other in silence as orbiting bodies move through light and shade. In every region, the same law continues without haste. Energy arrives, energy departs, and matter responds. Inside that response, atoms tremble a little less. Molecules drift a little more slowly. Solids hold themselves more tightly. Gases spread with less agitation. The cold of space is therefore never only around things. It comes to rest within them. It lowers motion, softens activity, and changes how matter keeps its form. What seems at first like a vast emptiness is also a patient physical process, always unfolding through radiation and balance. This makes the cold of space less dramatic than it first appears, and more profound. It is not a sudden force waiting to seize whatever enters. It is a condition shaped by time, exposure, material, and scale. It works without sound, without urgency, and without pause. From the outermost background of the universe to the hidden motion inside a grain of dust, the same quiet order remains. In that order, space is cold not because it is cruel, but because it is open. Heat escapes, light weakens with distance, motion settles, matter grows stiller, though never perfectly still. And the universe, in its vast calm, keeps cooling,